There is a photograph that sits on my desk, not a particularly special photograph, just a moment from a summer afternoon, light filtering through trees, shadows stretching across grass, a child's hand reaching toward something out of frame. The photograph was taken 7 years ago, 7 years that now exist only as memory, as neural patterns, as stories we tell ourselves about what happened. Those 7 years are gone. They existed, and now they do not exist in the same way they once did. They have become the past. We understand this intuitively. The present moment continuously transforms into something we call the past, and that past appears to stretch backward through time, through years, through centuries, through millennia, getting dimmer and more distant until eventually we reach a point where our records fail, where our knowledge gives way to educated guessing, and then finally to the limits of what we can know at all. And for more than half a century now, we have been told with increasing confidence that if we trace this backward journey far enough, we arrive at a beginning. Not just a beginning of human history, or of Earth, or even of our galaxy, a beginning of everything, a moment 13.8 billion years ago, when the entire observable universe, all of space itself, all of time, all of matter and energy, erupted from an infinitesimally small point in an event we have come to call the Big Bang. The Big Bang has entered our culture as a kind of creation story for the scientific age. It appears in textbooks as established fact. It anchors our cosmic timeline. It provides an answer to the most fundamental question children ask when they first grasp the concept of sequence and causality: what came before everything else? The answer we give them is simple: nothing came before. The Big Bang was the beginning. There was no before the Big Bang because time itself began at that moment. Asking what came before the Big Bang is like asking what's north of the North Pole. The question contains a logical impossibility. Space and time emerged together, and nothing that we would recognize as existence preceded that emergence. This is the story. This is the assumption that grounds virtually all of modern cosmology, and it is an assumption built on extraordinary evidence. Evidence so compelling, so mathematically precise, so observationally verified that doubting the Big Bang itself would be foolish. But there is a difference between doubting the Big Bang and questioning whether the Big Bang was truly a beginning. That difference matters. It matters philosophically, of course, but more importantly for our purposes, it matters physically. Because as our understanding of fundamental physics has deepened over the past few decades, as we have pushed our theories into more extreme regimes and confronted more profound puzzles, a strange thing has happened. The absolute certainty that the Big Bang represents the beginning of all things has begun to soften around the edges. Not because the evidence for the Big Bang has weakened, quite the opposite, but because the very concept of an absolute beginning has become, in the language of physics, problematic. The problem isn't with the Big Bang as an event. The problem is with the word beginning. To understand why this word has become problematic requires us to think carefully about what we mean by time, by causality, by existence itself. It requires us to examine the foundations of our two great theories of physics, general relativity and quantum mechanics, and to confront the uncomfortable fact that these theories, which work so magnificently in their respective domains, appear to contradict each other at the most fundamental level. And it requires us to consider possibilities that seem, at first encounter, absurd, possibilities that challenge not just our scientific models, but our basic intuitions about the nature of reality. What if the Big Bang was not a beginning, but a transition? What if the state we call the Big Bang was itself the result of something prior? Something that existed in a form so different from our current universe that we struggle even to describe it. What if the universe did not begin, but rather has existed in some form, perhaps a very different form, for far longer than 13.8 billion years, perhaps forever. These are not idle philosophical speculations. These are serious scientific questions grounded in real theoretical work being done by physicists and cosmologists at the forefront of their fields. They are questions that emerge naturally when we take our best physical theories and push them to their limits. Questions that cannot yet be answered, but which cannot be dismissed either. This is not a story about certainty. It is a story about the boundary between what we know and what we can know, about the strange region where physics meets philosophy, where mathematics suggests possibilities that our intuition rejects, where the universe may be far stranger than we have yet imagined. We are going to trace backward through time, just as we traced backward from that summer photograph. But unlike that simple exercise in memory, this journey will not lead us to a clear beginning. Instead, it will lead us to a question that remains even now genuinely open. What if the Big Bang wasn't the beginning? Let us begin with time itself, not time as we experience it, the relentless forward march of seconds and hours, but time as a physical dimension, as something that can be measured, warped, stretched, and perhaps even created. We are accustomed to thinking of time as a universal backdrop against which events occur. We imagine a great cosmic clock ticking away uniformly, providing the same now for the entire universe. This intuition is so deeply embedded in our thinking that we rarely question it. But this intuition is wrong, provably, demonstrably, observationally wrong. Einstein's special relativity revealed more than a century ago that time is not absolute. Time is relative. It flows at different rates depending on how fast you are moving. Two observers traveling at different speeds will disagree about the duration between events, will disagree about whether two distant events are simultaneous, will even disagree about the order in which certain events occur. This is not a matter of perception or measurement error. This is the fundamental nature of time in our universe. General relativity deepened this revolution. Einstein showed that gravity is not a force in the traditional sense, but rather a curvature of space-time itself. Mass and energy warp the fabric of space and time around them. Near a massive object, time flows more slowly than it does far from that object. This has been measured repeatedly with extraordinary precision. Clocks at different altitudes on Earth tick at measurably different rates. An astronaut orbiting ages slightly less than their twin on the ground, not metaphorically, but literally, measurably, physically. This relativistic nature of time creates immediate problems when we try to speak about the beginning of the universe. Imagine we wind the clock backward. We observe that galaxies are moving away from each other. This is Hubble's great discovery, the expansion of the universe. We can calculate their velocities, measure their distances, and run the film in reverse. If galaxies are moving apart now, they must have been closer together in the past. Running this logic to its conclusion leads us to a moment approximately 13.8 billion years ago, when all the matter and energy in the observable universe was compressed into an incredibly small, incredibly hot, incredibly dense state. This is the Big Bang, or more precisely, this is the earliest moment we can describe using general relativity. As we approach this moment, as the density and temperature increase, the universe we calculate becomes stranger and stranger. The equations of general relativity tell us that at some point, at the very beginning of this backward journey, the density becomes infinite, the temperature becomes infinite, the curvature of space-time becomes infinite. All our physical quantities diverge to infinity. This is what physicists call a singularity. The word singularity sounds exotic, almost mystical, but its meaning in physics is quite precise and quite troubling. A singularity is a point where our equations break down, where they produce infinite values, where they cease to make predictions. The appearance of a singularity in a physical theory is not a sign that something interesting is happening. It is a sign that the theory has been pushed beyond its domain of validity. It is the universe's way of telling us, your description has failed. Think of it this way. If you are calculating the trajectory of a thrown ball, Newtonian physics works beautifully. The equations are simple, the predictions are accurate. But if you try to use those same Newtonian equations to describe what happens to that ball as it approaches the speed of light, the equations give nonsensical answers. They predict that the ball's mass becomes infinite, that time dilation becomes infinite. These infinities don't mean that something special happens at the speed of light. They mean that Newtonian physics is the wrong tool for this regime. You need special relativity. The singularity at the Big Bang is, many physicists now believe, exactly this kind of signal. Not a description of what actually happened, but an indication that general relativity, the very theory that led us to the Big Bang in the first place, cannot be trusted in this extreme regime. But there is a deeper problem, one that goes beyond the mathematical breakdown of general relativity. It has to do with causality itself. Causality is the principle that effects follow from causes, that events are linked by chains of cause and effect extending through time. We see causality everywhere in our experience. The glass falls because you knocked it. The plant grows because it receives sunlight. Your memory of yesterday exists because yesterday actually occurred. Causality is so fundamental to our thinking that we can barely conceive of a universe without it. But causality requires time. It requires a before and an after. It requires a sequence of events. And if the Big Bang was the beginning of time itself, then there was no before the Big Bang. There was no prior state from which the Big Bang emerged. There was no cause of the Big Bang because cause and effect themselves only make sense within time, and time began with the Big Bang. This is the standard answer given when someone asks what caused the Big Bang. The question itself is declared meaningless. It is the North Pole argument. There is no before, just as there is no north of the North Pole. But this answer, while logically consistent within general relativity, feels unsatisfying. Not emotionally, science need not satisfy our emotional intuitions, but physically. It asks us to accept that causality, which governs every other physical process we have ever studied, simply does not apply at the most important moment in cosmic history. It asks us to accept that the universe emerged from nothing, preceded by nothing, caused by nothing, for no reason at all. Perhaps more troubling, it asks us to accept that time itself had a beginning, that there was a first moment. But what does it mean for time to begin? In our normal experience, beginnings happen within time. The concert begins at 8 o'clock. The Ice Age began 2.6 million years ago. A process starts, and we can point to the moment when it was not happening and the moment when it was happening. And there is a transition between these states. But the beginning of time itself cannot be this kind of beginning. There cannot be a moment when time was not happening and then a moment when it was happening, because that very description requires time to already exist. The beginning of time is not an event within time. It is, and here language truly begins to fail us, it is something else entirely. Physicists sometimes use the word emergence to describe this. Time emerges at the Big Bang. Space-time itself emerges, but emergence is usually understood as a process, and processes unfold in time. The emergence of time cannot unfold in time. It is either instantaneous, a word that itself presupposes time, or it is not a temporal process at all. We are confronting the limits of language here, and language reflects the limits of our conceptual framework. Our brains evolved to navigate a world where time flows at a human pace, where causes precede effects by observable intervals, where beginnings are moments we can point to. We did not evolve to think clearly about the origin of time itself. But physics is not limited by what we find intuitive. Physics follows the mathematics, follows the evidence, follows the logic wherever it leads. And when we follow that logic carefully, when we examine what our best theories actually tell us about the Big Bang, we find something unexpected. We find that the idea of an absolute beginning, a first moment of time, a singularity from which everything emerged, is not a conclusion forced upon us by the evidence. It is an assumption built into general relativity, but one that may not survive when we incorporate quantum mechanics into our description. The question is not whether the Big Bang happened. The evidence for the Big Bang is overwhelming. The question is whether the Big Bang was the beginning or whether it was something else, a boundary, a transition, a phase in a longer history. To explore that question, we need to understand where our current theories break down. We need to understand the regime where general relativity and quantum mechanics collide. We need to understand what happens when physics itself breaks. There is a scale in physics that most people have never heard of, despite it being perhaps the most important scale in all of fundamental science. It is called the Planck scale, named after Max Planck, the physicist who first stumbled upon the quantum nature of reality in the year 1900. The Planck scale is not a place, it is a regime of such extreme density, such extreme energy, such extreme curvature of spacetime that both quantum mechanics and general relativity become equally important. And in that regime, something goes profoundly wrong. Let us establish some numbers, though the numbers themselves are less important than what they represent. The Planck length is approximately 10% to the negative 35 meters. This is incomprehensibly small. An atom is about 10 to the negative 10 meters across. A proton is about 10 to the negative 15 meters. The Planck length is 20 orders of magnitude smaller than a proton. It is a billion times smaller than anything we have ever observed directly. The Planck time is the time it takes light to cross one Planck length, approximately 10 to the negative 43 seconds. For comparison, the fastest processes we can currently measure occur on timescales of around 10 to the negative 18 seconds. The Planck time is more than 20 orders of magnitude shorter than this. The Planck energy is the energy required to probe physics at the Planck length. It is about 1 billion joules, roughly the kinetic energy of a small car traveling at 60 miles per hour, but compressed into a single quantum particle. No particle accelerator we could ever build, even in principle, could reach Planck energies. The most powerful accelerator we have, the Large Hadron Collider, reaches energies about 10 trillion times smaller than the Planck energy. These scales might seem like abstract curiosities, irrelevant to anything practical, but they are not irrelevant to cosmology. Because when we trace the universe backward from its current, expanded state, calculating the density and temperature and energy, as we go, we reach the Planck regime not at some distant hypothetical moment, but at a very specific time in cosmic history. We reach the Planck regime approximately 10 to the negative 43 seconds after the Big Bang, one Planck time after the singularity. This is where everything we think we understand falls apart. General relativity is our theory of space-time, of gravity, of the large-scale structure of the cosmos. It describes how mass and energy curve space-time, how that curvature manifests as what we call gravity, how the universe expands and evolves. General relativity has been tested exhaustively. It predicts the orbit of Mercury, the bending of light by the sun, the gravitational redshift of photons climbing out of deep gravitational wells. It predicted gravitational waves decades before they were observed. It is, by any reasonable measure, one of the most successful theories in the history of science. But general relativity is a classical theory. It treats space-time as a smooth, continuous fabric. It assumes that you can always, in principle, measure positions and times with arbitrary precision. It does not incorporate the fundamental randomness, the intrinsic uncertainty, the discrete quantum jumps that characterize the microscopic world. Quantum mechanics, conversely, is our theory of the very small. It describes how particles behave as waves, how measurements force systems into definite states, how uncertainty is not a limitation of our instruments, but a feature of nature itself. Quantum mechanics governs chemistry, atomic physics, particle physics. It has been tested even more exhaustively than general relativity. Every piece of electronics, every laser, every understanding of why matter is stable, all of it rests on quantum mechanics. But quantum mechanics, in its standard formulation, treats spacetime as a fixed, flat background. It does not account for the curvature of spacetime. It does not incorporate gravity in any fundamental way. For almost all practical purposes, this mutual incompatibility does not matter. General relativity dominates at large scales. Stars, galaxies, the cosmos. Quantum mechanics dominates at small scales. Atoms, particles, fields, the regimes do not overlap. A physicist studying the behavior of electrons does not need to worry about the curvature of spacetime. A cosmologist studying the evolution of galaxies does not need to worry about quantum uncertainty in the positions of stars. But there is one place where these regimes cannot be separated. There is one situation where both the quantum world and the gravitational world become equally important, where neither theory can be ignored. That situation is the Planck regime. And the universe existed in the Planck regime during the first moments after the Big Bang. What happens in the Planck regime? We do not know. Truly, honestly, we do not know. We have no theory of quantum gravity, no theory that successfully merges quantum mechanics and general relativity into a single consistent framework. We have candidates. String theory is one. Loop quantum gravity is another. There are others still, each with their own mathematical elegance and their own unsolved problems. But we do not have a confirmed, tested, experimentally verified theory of quantum gravity. And without such a theory, we cannot describe what actually happens at the Big Bang itself. We can trace cosmic history back to one Planck time after the nominal beginning. But that final Planck time, that final frontier between the universe we can describe and the singularity we cannot, remains veiled. The singularity predicted by general relativity, that point of infinite density and infinite curvature, is almost certainly an artifact, not a real feature of the universe, but a mathematical indication that general relativity has been pushed beyond its breaking point. The singularity is where we must incorporate quantum effects, and quantum effects, we have strong reasons to believe, smooth out infinities. Consider the simplest example from quantum mechanics, the hydrogen atom. In classical physics, an electron orbiting a proton should spiral inward, radiating energy until it crashes into the nucleus. The classical theory predicts a catastrophe, an instability. But quantum mechanics tells us that electrons cannot occupy arbitrary positions. They exist in discrete energy levels, in specific quantum states. There is a ground state, a lowest energy level, below which the electron cannot fall. Quantum mechanics prevents a classical catastrophe. Something similar, many physicists believe, must happen at the Big Bang. The singularity predicted by classical general relativity, like the classical electron spiraling into the nucleus, is an artifact of using the wrong theory. When quantum effects are properly included, the singularity should be replaced by something else, something that might be extreme but not infinite, something that might be describable even if we do not yet have the tools to describe it. But here is where the question of the beginning becomes truly interesting, because there are multiple ways that quantum gravity might resolve the singularity, and these different ways have radically different implications for what the Big Bang actually was. One possibility is that quantum gravity smooths out the singularity into a very small but finite size. In this scenario, the universe did begin at the Big Bang, but there was no infinite density, no true singularity. Instead, there was a smallest possible size, perhaps the Planck length, and the universe began in this smallest possible state and expanded from there. Time still begins at the Big Bang, but the beginning is gentler, less pathological than the classical singularity would suggest. This is often considered the conservative possibility, the minimal modification to our current picture. But there is another possibility, one that has gained serious attention over the past few decades. What if the quantum effects that resolve the singularity do more than just smooth it out? What if they actually eliminate the boundary altogether? What if the mathematics of quantum gravity, when properly formulated, simply does not allow for a beginning at all? This possibility is not science fiction. It emerges naturally from several approaches to quantum gravity. In some versions of loop quantum gravity, for instance, the equations that describe how the universe evolves do not have a starting point. The volume of the universe approaches a minimum value but never reaches zero. The Big Bang in these models is not a beginning but a bounce. A moment of minimum size, yes, but a moment preceded by a contracting phase, a prior epoch during which the universe was collapsing. In such a scenario, the Big Bang is a transition, a quantum bridge between a contracting universe and an expanding one. What we see as the beginning is, from a larger perspective, merely the middle of a longer story. Other approaches suggest other possibilities. In certain formulations of quantum cosmology, an approach that attempts to apply quantum mechanics to the universe as a whole, the question, what happened before the Big Bang, becomes ill-defined, not because there was no before, but because the quantum state of the universe is fundamentally timeless. Time emerges from this timeless quantum state, and the emergence happens in such a way that there is no beginning, only a gradual transition from a regime where time does not exist in the usual sense to a regime where it does. These ideas are speculative. They are based on incomplete theories. They make predictions that are, in most cases, impossible to test with current technology. But they are not idle speculation. They are serious attempts to solve a real problem, the problem of the singularity, using the best tools theoretical physics has developed. And they all share a common feature. They suggest that the Big Bang, rather than being an absolute beginning, was a kind of boundary, a boundary not in time, but in our description, a place where one mode of existence transitioned into another. The universe might extend beyond this boundary, not forward or backward in time, perhaps, but in some other way that our current language struggles to articulate. What that other way might be depends on which approach to quantum gravity turns out to be correct. But the possibility itself, the possibility that there is something beyond the Big Bang, is taken seriously by a significant portion of the theoretical physics community. This brings us to a crucial realization. For decades, cosmology presented us with a simple choice. Either the universe began at the Big Bang, or it has existed forever in some form. The first option seemed problematic philosophically, but was supported by general relativity. The second option seemed to solve the philosophical problem, but lacked a physical mechanism. But quantum gravity offers a third option. The universe might not have a beginning in the usual sense, but it also might not have existed forever in the same form. It might have existed in some prior state, some pre-Big Bang configuration that was so different from our current universe that we cannot yet describe it adequately. The Big Bang might mark not the creation of the universe, but the creation of the universe as we know it, the creation of classical space-time, the beginning of the cosmic history we can trace before the Big Bang, if before is even the right word. There might have been something else. What that something else was is the question we must now explore. The idea that the Big Bang might not be the absolute beginning is not new. It has roots that stretch back decades, long before modern quantum gravity gave these ideas mathematical flesh. What has changed is not the existence of these ideas, but their status. They have moved from the fringe of cosmology to the mainstream, from philosophical speculation to serious scientific investigation. Let us consider the oldest of these ideas, the cyclic universe. The notion that the universe moves through cycles, expanding, contracting, perhaps bouncing back into a new expansion, has ancient philosophical roots. Hindu cosmology speaks of cycles of creation and destruction spanning vast timescales. Nietzsche proposed eternal recurrence, but these were philosophical or religious frameworks, not physical theories. The modern scientific version of the cyclic universe began in the middle of the 20th century, when cosmologists first seriously confronted the possibility that the expansion of the universe might eventually reverse. General relativity allows for different possible fates of the universe depending on the amount of matter and energy it contains. If there is sufficient matter, the gravitational attraction between all the galaxies should eventually overcome the expansion, causing the universe to contract. This contraction would accelerate, becoming faster and faster, until ultimately everything collapses back into a hot, dense state, a big crunch, the time reverse of the Big Bang. But what happens at the big crunch? The equations of general relativity predict, once again, a singularity, just as they do at the Big Bang. And just as at the Big Bang, this singularity represents a breakdown of the theory. For many years, the big crunch was simply considered the end. The universe would expand, reach a maximum size, contract, and terminate in a singularity. End of story. But some physicists began to wonder if quantum gravity might resolve the Big Bang singularity and replace it with something non-singular. Might it do the same at the Big Crunch? And if the Big Crunch singularity is resolved, might the universe not end at all, but instead bounce, beginning a new cycle of expansion? This led to models of a bouncing universe, a universe that expands from a Big Bang, reaches a maximum size, contracts to a big crunch, but then bounces at the moment of maximum contraction, emerging into a new Big Bang. And if this happened once, why not infinitely many times? Perhaps our Big Bang was not the first. Perhaps it was merely the most recent in an infinite series of bounces, each cycle looking much like the others, the universe eternally oscillating between expansion and contraction. This is an appealing picture in some ways. It eliminates the problem of the beginning. There is no beginning, just an infinite series of cycles. It eliminates the problem of the end. There is no end either. The universe becomes eternal, not static but dynamic, forever transforming but never truly beginning or ending. But the cyclic model faces significant challenges. One is entropy. The second law of thermodynamics tells us that entropy, roughly speaking, disorder, always increases in any closed system. If the universe goes through repeated cycles, entropy should build up from cycle to cycle. Each new cycle should start with higher entropy than the previous one. Over infinite cycles, the universe should approach maximum entropy, a state of thermal equilibrium where nothing interesting can happen. This is sometimes called the heat death of the universe, and it seems incompatible with an eternal cyclic model that produces the same kind of low entropy Big Bang over and over again. Some versions of cyclic cosmology attempt to address this by proposing that the universe grows larger with each cycle, diluting the entropy, effectively resetting the system. Others invoke more exotic mechanisms. But the entropy problem remains a serious challenge. Another challenge is observational. Current evidence suggests that the expansion of the universe is accelerating, driven by something we call dark energy. If this acceleration continues indefinitely, the universe will never recollapse. There will be no big crunch, no bounce, no cycle. The universe will expand forever, becoming ever more dilute, ever colder, eventually reaching a state where all structure has dissipated. The cyclic model, at least in its simple form, appears to be ruled out by observations. But this has not ended interest in cyclic ideas. It has simply forced theorists to become more creative. Modern cyclic models often invoke extra dimensions of space, dimensions beyond the three we experience, and suggest that our Big Bang was caused by the collision of higher dimensional structures called brains. In these models, inspired by string theory, two brains move through a higher dimensional space, periodically colliding. Each collision produces a Big Bang in the three-dimensional space we inhabit. The cycles continue not because our three-dimensional universe contracts and bounces, but because the brains separate and then collide again. These models are highly speculative. They require string theory to be correct, and string theory remains unverified. They require extra dimensions which we have never observed. They make predictions that are extraordinarily difficult to test, but they are mathematically consistent, and they demonstrate that the cyclic idea can be formulated in ways that avoid some of the classical problems. A different approach to what came before the Big Bang involves eternal inflation. This idea emerged from inflationary cosmology, which was developed in the 1980s to solve certain puzzles about the Big Bang. Standard Big Bang cosmology had problems explaining why the universe appears so uniform on large scales and why space appears so flat. Inflation solved these problems by proposing that in the first fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion, growing by a factor of at least 10 to the 26 in a time period of around 10% to the negative 32 seconds. This brief but violent expansion smoothed out any initial irregularities and flattened space, explaining the uniformity and flatness we observe. Inflation was a tremendous success. It made predictions, specific patterns in the cosmic microwave background radiation that have been confirmed by observations. It became part of the standard model of cosmology. But inflation also raised new questions, and one of the deepest was this: if inflation started, how does it stop? Inflation is driven by a field called the inflaton field. This field has energy, and that energy drives the rapid expansion. Eventually, the inflaton field decays. Its energy is converted into particles and radiation, and normal expansion takes over. This decay process is called reheating, and it marks the end of inflation and the beginning of the hot Big Bang that we observe. But here is the key insight. The decay of the inflaton field is a quantum process. It does not happen everywhere at once. Different regions of space stop inflating at different times, randomly, according to quantum probabilities. And crucially, While some regions are stopping, others are still inflating, and those inflating regions are expanding exponentially, creating ever more space. The result is a fractal, ever growing structure. Most regions stop inflating and become pocket universes like our own, filled with matter and radiation, expanding at a normal rate. But scattered throughout this vast expanse, islands of space continue to inflate, growing exponentially, each eventually producing its own multitude of pocket universes. This process, once it starts, never stops. It is eternal to the future. But if eternal inflation is eternal to the future, was it eternal to the past as well? Did inflation have a beginning, or has it been happening forever? This question led to intense debate. Some physicists argued that eternal inflation, if it occurred at all, must have begun at the Big Bang. Others argued that if inflation can be eternal to the future, it might be eternal to the past as well, with no beginning at all. In the early 2000s, a theorem, proved by three physicists, Arvind Borde, Alan Guth, and Alexander Vilenkin, appeared to settle this question. The Borde-Guth-Vilenkin theorem showed that any eternally inflating universe, if you trace it backward in time, must have had a boundary in the past, a beginning. You cannot have eternal inflation extending infinitely far into the past. Somewhere there must be a starting point. This result was widely interpreted as proof that the universe must have had a beginning, that even in eternally inflating models, you cannot escape the need for a Big Bang. But the theorem has subtleties. It assumes that the average expansion rate is always positive as you go back in time. If there is a phase of contraction, or if quantum gravity modifies the structure of space-time in the very early universe, the theorem might not apply. The theorem tells us that classical, ever-expanding space-time cannot be eternal to the past. It does not tell us that there was nothing before the Big Bang. It only tells us that whatever came before cannot be described as classical eternal inflation. This has led some theorists to propose that eternal inflation was preceded by something else. Perhaps a contracting phase that transitioned into inflation. Perhaps a quantum timeless state from which inflation emerged. Perhaps something stranger still, something that requires quantum gravity to describe. The point is this: eternal inflation strongly suggests that our Big Bang was not unique. If inflation occurred and led to the creation of our pocket universe, it likely led to the creation of countless other pocket universes, each with potentially different physical properties, different constants of nature, different histories. We would exist in a vast multiverse, with our observable universe being just one small region in an eternally inflating expanse. But even eternal inflation, as vast and strange as it is, might not be the whole story. It might itself have emerged from something prior. There is yet another idea, more radical still, the idea that time itself, as we understand it, does not exist at the most fundamental level, that time is an emergent phenomenon, arising from something deeper, something timeless. This idea appears in several approaches to quantum gravity. In loop quantum cosmology, for instance, time emerges from the evolution of quantum geometry. In some formulations of string theory, the fundamental equations are time-symmetric, with no preferred direction to time. In the Wheeler-DeWitt equation, an attempt to apply quantum mechanics to the entire universe, there is no time variable at all. The equation describes a timeless quantum state, and time emerges only when we consider certain types of measurements or certain limiting cases. If time is emergent, then the question, what came before the Big Bang, might be asking the wrong thing. There might be no before, not because time began at the Big Bang, but because before and after are concepts that only make sense in the emerged classical regime. At the most fundamental level, the universe might be described by a timeless quantum state, and the Big Bang might represent the point at which time began to emerge from this timeless foundation. This is extraordinarily difficult to visualize. We are creatures of time. Our every thought, our every experience is structured by the flow of time. The idea that time itself is not fundamental, that it emerges from something timeless, challenges our ability to conceptualize reality. And yet, it might be true. These ideas, cyclic universes, eternal inflation, emergent time, are not mutually exclusive. Different aspects might be correct. The universe might have both cyclic features and eternally inflating features. Time might be emergent, and the emerged time might exhibit cycles or bounces. We are still piecing together the puzzle, and we do not yet know what the final picture will look like. What we do know is this: the simple story of the Big Bang as an absolute beginning, while consistent with classical general relativity, becomes much more complicated when we incorporate quantum mechanics and push our theories to their limits. Multiple serious scientific frameworks suggest that the Big Bang might not have been the beginning, and while none of these frameworks is yet proven, none can be easily dismissed either. The evidence is incomplete, the theories are speculative. But the question remains open, genuinely open, in a way it was not open 50 years ago. What if the Big Bang wasn't the beginning? The honest scientific answer is, we do not know, but it is possible, perhaps even likely. Let us suppose, for the sake of exploration, that the Big Bang was not the beginning, that there was something before, a prior state, a pre-universe, a quantum form, a collapsing precursor, an eternal inflation, a timeless mathematical structure that gave birth to time. Let us suppose that the boundary we call the Big Bang was not the origin of all things but a transition between one mode of existence and another. What would this mean? Not just for cosmology, but for our understanding of existence itself. The implications are layered. Some are straightforward, almost technical. Others reach into philosophy, into questions about the nature of reality and our place within it. Begin with entropy. Entropy is a measure of disorder, of the number of possible microscopic arrangements that correspond to a given macroscopic state. The second law of thermodynamics tells us that entropy increases over time in any closed system. Systems evolve from ordered states to disordered states. Heat flows from hot to cold, never the reverse. Eggs break but do not spontaneously reassemble. The past is characterized by lower entropy, the future by higher entropy, and this asymmetry is what gives time its direction, its arrow. The Big Bang, as we currently understand it, began in a state of extraordinarily low entropy. The early universe was hot and dense. Yes, but it was also remarkably uniform, remarkably smooth. There were tiny quantum fluctuations, but on large scales, the universe was almost perfectly homogeneous. This uniformity represents low entropy. As the universe evolved, gravity amplified those tiny fluctuations, causing matter to clump into stars and galaxies, creating structure. And structure creation is entropy creation. The universe today, with all its galaxies and black holes and vast cosmic voids, has far higher entropy than the universe shortly after the Big Bang. This entropy gradient, from low to high, explains why we remember the past but not the future, why causes precede effects, why time feels like it flows in one direction. The arrow of time is rooted in the second law of thermodynamics, which in turn is rooted in the fact that the Big Bang was a low entropy state. But this raises a profound question. Why did the Big Bang have such low entropy? Why did the universe begin in such a special, finely tuned, improbable state? In a universe that began with the Big Bang, there is no answer to this question. The low entropy is simply a boundary condition, an initial condition that we must accept without explanation. Some physicists have proposed anthropic arguments. Only in a universe with low initial entropy could complexity, life, and observers arise. so we should not be surprised to find ourselves in such a universe. But this explanation, while logically valid, feels incomplete. It explains why we observe low initial entropy, but not why low initial entropy was possible in the first place. If there was something before the Big Bang, however, the question might have an answer. If the Big Bang was a bounce, for instance, the low entropy might be explained by the dynamics of the bounce itself. Some models of bouncing cosmology suggest that the bounce process naturally produces a state of low entropy, effectively resetting the entropic clock. Other models, particularly those involving eternal inflation, suggest that the low entropy of our Big Bang is not special at all. It is simply one outcome among countless others, with other Big Bangs in other regions of the multiverse, starting with different entropy levels. The point is not that we have a definitive answer, but that the existence of a pre-Big Bang state opens up the possibility of explanations that are foreclosed if the Big Bang was the absolute beginning. Consider next the nature of physical laws. In our current understanding, the laws of physics, the equations that govern how matter and energy behave, the constants that appear in those equations, are simply given. They are part of the fundamental description of our universe, and we discover them through observation and experiment, but we do not have a deeper explanation for why these laws hold rather than some other set of laws. If the Big Bang was the beginning, this seems inevitable. Laws exist, and we inhabit a universe where these particular laws obtain. There is no why, only what. But if there was something before the Big Bang, the question becomes more interesting. Were the laws the same before the Big Bang, or might the laws themselves have been different, with our current physical laws emerging only at the Big Bang or shortly thereafter? This is not idle speculation. Some approaches to quantum cosmology suggest that the effective laws of physics can change as the universe evolves through different regimes. In very early times, at extremely high energies, symmetries might be present that are broken as the universe cools. The fundamental constants might not be constant across all epochs. What we perceive as fundamental might be emergent, contingent on the specific state and history of the universe. If this is true, then the laws of physics as we know them might be local not in space, but in cosmic history. They might describe only the post-Big Bang universe, the universe in the classical regime where space-time has emerged and settled into its current structure. The pre-Big Bang state might have been governed by different mathematics, different principles, different symmetries. This has profound implications for the quest for a theory of everything, a single unified framework that explains all physical phenomena. If such a theory exists, it would need to be more general than the specific laws we observe in our universe. It would need to encompass not only our universe, but also any prior state, any transition, any other possible configurations of reality. The theory of everything would be a theory of all possible universes, not just ours. Then there is the question of causality. We have already discussed how causality becomes problematic at the Big Bang if the Big Bang is the beginning. But if there is a before, causality might extend across the boundary. The Big Bang might have a cause. This does not mean a first cause in the traditional philosophical sense. The chain of causation might extend backward indefinitely through an infinite series of prior states with no ultimate origin, or it might loop back on itself in some way that our linear conception of time cannot capture. But it would mean that the Big Bang was not an uncaused event, not a brute fact, but rather the result of prior physical processes. Some physicists find this prospect deeply satisfying. It restores a kind of explanatory closure, a sense that the universe is comprehensible all the way down, with no arbitrary beginning that defies explanation. Others are less certain, pointing out that an infinite regress of causes is no less mysterious than an uncaused beginning. merely different. And then there are the philosophical implications, the existential questions that arise when we contemplate the possibility that the Big Bang was not the beginning. If the universe did not begin, if it has existed in some form for an infinite duration, or if time itself is emergent and the question of duration does not apply, then what does this say about the nature of existence? Is existence necessary or is it contingent? A universe that begins seems contingent. It did not have to exist. Something caused it to begin, or it began spontaneously, but either way, there was a transition from non-existence to existence. The universe is a thing that happened, not a thing that must be. But a universe that has always existed in some form starts to feel different. Not necessary in the logical sense, it is still conceivable that nothing might have existed instead, but necessary in a deeper, perhaps physical sense. Existence becomes the default state, not an exception requiring explanation. This distinction matters for how we think about reality. It matters for the question of why there is something rather than nothing, a question that has occupied philosophers for millennia. If the universe began, the question remains as stark as ever. If the universe did not begin, the question shifts. It becomes not why is there something, but what is the nature of the something that exists. There is also the question of meaning. Human beings seek meaning, and we often locate meaning in origins and endings, in beginnings and purposes. A universe with a definite beginning and a definite end has a narrative arc. It is a story with a start and a finish. Our existence, brief as it is on cosmic scales, is at least situated within a larger story. But a universe that has always existed, or that cycles endlessly, or that is part of an eternal multiverse, does not have this narrative structure. There is no ultimate beginning, no final end, just an ongoing process, perhaps without direction, perhaps without meaning. For some, this is profoundly liberating. It removes the burden of cosmic purpose, allows us to create our own meaning without reference to some grand design. For others, it is unsettling, even nihilistic. A universe without beginning or end can feel cold, indifferent, empty of significance. These reactions are deeply personal. Science does not tell us how to feel about the universe. It tells us what the universe is like, as best we can determine, and then we must each decide what that means to us. But it is worth noting that the question of whether the Big Bang was the beginning is not purely abstract. It touches on these deeper questions about existence, meaning, and our place in the cosmos. It matters not just for cosmology, but for how we understand ourselves. There is one more implication to consider, perhaps the most practical one: testability. If there was something before the Big Bang, might we be able to detect evidence of it? This might seem impossible. The Big Bang appears to be a nearly perfect barrier to information. The hot, dense conditions in the early universe should have erased any traces of what came before, much as the heat of a fire erases information about what was burned. But nearly perfect is not the same as perfect. Some models of pre-Big Bang cosmology make predictions that differ subtly from standard Big Bang cosmology. These differences might be encoded in the cosmic microwave background radiation, in the pattern of temperature fluctuations across the sky, in the polarization of light, in the spectrum of gravitational waves from the early universe. Observational cosmology has become extraordinarily precise in recent decades. We can measure the cosmic microwave background with exquisite detail. We can detect gravitational waves. We can map the large-scale structure of the universe. And some of these measurements have revealed small anomalies, features that do not quite match the predictions of the simplest models. Most of these anomalies are likely statistical flukes or the result of systematic errors in the data. But some might be real. And if they are real, they might be hints of physics beyond the standard Big Bang model, hints perhaps of what came before. This is speculative. The evidence is not strong enough to draw firm conclusions, but it is tantalizing. It suggests that the question of what came before the Big Bang might not be forever beyond our reach. It might be, to some degree, testable. If we could confirm that there was a before, that the Big Bang was not the beginning, it would not answer all our questions. It would raise new ones. What was the nature of the pre-Big Bang state? How did the transition occur? Are there laws that govern the transition? Could there be multiple transitions, multiple Big Bangs, a vast cosmic history extending far beyond what we can currently observe? But it would fundamentally change our understanding of the universe. It would shift the Big Bang from the origin of all things to a phase transition, a critical moment, but not the first moment. It would open up the possibility of a richer, deeper, more complex cosmic history. It would tell us that the universe is even stranger, even more mysterious than we had imagined. And in science, that is always a sign that we are on the right track. The universe does not owe us simplicity. It does not owe us closure. It is what it is, and our job is to follow the evidence, to push the theories, to ask the difficult questions, even when the answers are not yet within reach. We began with an assumption. The assumption that the Big Bang was the beginning, that 13.8 billion years ago everything, space, time, matter, energy, came into existence in an event without precedent or cause. This assumption has guided cosmology for more than half a century. It has been enshrined in textbooks, popularized in documentaries, accepted as fact by most of the public and most of the scientific community. But, as we have seen, this assumption rests on a foundation that becomes increasingly uncertain the closer we examine it. It rests on classical general relativity, a theory that breaks down the Planck scale. It rests on the idea that singularities are physical rather than mathematical artifacts. It rests on a particular understanding of time, of causality, of what constitutes a beginning. When we incorporate quantum mechanics, when we take seriously the implications of quantum gravity, when we follow the mathematics of our best theories into the extreme regime of the very early universe, the certainty dissolves. We are left not with a definitive answer, but with multiple possibilities, each strange in its own way, none fully developed, none yet confirmed or ruled out by observation. The Big Bang might have been a bounce from a prior contracting phase. It might have been one event in an eternal cycle. It might have emerged from a timeless quantum state, with time itself beginning at that moment, not because there was nothing before, but because before is a concept that only makes sense after time has emerged. It might have been preceded by eternal inflation, our universe one pocket among countless others in a vast and growing multiverse, or it might have been something else entirely, something we have not yet imagined because we lack the conceptual tools, the mathematical framework, the observational data to guide our imagination. This uncertainty is not a failure of science. It is a reflection of where we stand, at the boundary of knowledge, peering into a regime that we can barely access even in theory, let alone in experiment. We are asking the deepest possible question about the nature of reality. Did existence begin, or has it always been? And we are asking this question with tools, mathematics, observation, reason, that have been extraordinarily successful in understanding the universe we can see, but which might be inadequate for understanding the universe at its most fundamental level. There is a photograph on my desk. I mentioned it at the beginning, a summer afternoon 7 years ago, now existing only as memory. We understand this intuitively, the way the present flows into the past, the way history extends backward, getting dimmer and more uncertain, until eventually we reach the limits of what we can know. For the universe, those limits are closer than we might wish. We can trace cosmic history back through billions of years, through the formation of galaxies and stars, through the synthesis of the first atoms, through the era when the universe was opaque with plasma, through the first minutes when nuclei were forged, through the first second when particles and antiparticles annihilated, through the first microsecond when quarks combined into protons and neutrons. We can trace it all the way back to a time less than a second after the normal beginning, when the universe was 1 trillion degrees and denser than an atomic nucleus. But that final Planck time, that final frontier between what we can describe and what we cannot, remains veiled. And beyond that veil, if there is anything beyond that veil, lies a mystery that might never be fully resolved. Perhaps that is as it should be. The universe is not obligated to make itself comprehensible to us. We are pattern-seeking creatures, storytelling creatures, creatures who crave beginnings and endings and explanations. But the universe is not a story. It is a physical system, governed by laws we have only partially uncovered, operating on scales both vast and tiny that defy our intuition. What we can say with confidence is this: the evidence for the Big Bang itself, as an event, as a hot, dense state approximately 13.8 billion years ago, is overwhelming. The expansion of the universe, the cosmic microwave background, the abundances of light elements, the large-scale structure of galaxies, all point to this conclusion with remarkable consistency. The Big Bang happened. That is not in question. What is in question is whether the Big Bang was the beginning. And that question remains open. It remains open because our theories break down at the crucial moment. It remains open because quantum gravity is not yet understood. It remains open because time itself, near the Planck scale, might not work the way it works in our everyday experience. It remains open because multiple theoretical frameworks suggest multiple possibilities, and we do not yet have the observational data to distinguish between them. But the question being open is not the same as the question being unanswerable. Science is slow, patient work. Theories are developed, refined, tested. Observations push into new regimes. Technologies improve. What seems beyond our reach today might become accessible tomorrow. Not quickly, not easily, but possibly. Already we have observational programs searching for subtle signatures in the cosmic microwave background, for patterns that might reveal the physics of the very early universe. Already we have gravitational wave detectors that might, in future generations, detect signals from the first moments after the Big Bang. Already we have theoretical frameworks that make predictions that differ from one another in ways that might eventually be testable. The question of what came before the Big Bang, if anything came before at all, might remain unanswered for decades. It might remain unanswered for centuries, or it might be answered in our lifetime by observations we have not yet imagined, by theories we have not yet developed. Either way, the question is worth asking. It is worth asking because it pushes us to examine our assumptions, to question what we think we know, to recognize the difference between what our theories describe and what reality actually is. It is worth asking because the answer, whatever it turns out to be, will reshape our understanding of existence itself. There is a particular kind of intellectual experience that comes from confronting a question that is both profound and unresolved. It is not the satisfaction of finding an answer, nor the frustration of finding that no answer is possible. It is something between these, a state of active uncertainty, of knowing that we do not know, of understanding the shape of our ignorance well enough to see the possibilities. This is where we stand with the question of the Big Bang as beginning. We stand in that space of active uncertainty, with our instruments pointed at the sky, our mathematics scrawled on chalkboards, our theories incomplete but suggestive, our imaginations stretched but not yet broken. The Big Bang might have been the beginning, it might have been a transition, it might have been a bounce, an emergence, one event in an eternal process. Time might have started then, or time might be a local, emergent phenomenon, with the fundamental reality being timeless and the Big Bang merely the point where time began to crystallize. We do not know. We might never know with absolute certainty. But we can ask the question, we can develop the theories, we can make the observations, we can follow the evidence wherever it leads. And in the following, in the asking, in the confrontation with our own limitations and the universe's mysteries, there is a kind of meaning, not the meaning of an answer, but the meaning of the search itself. The recognition that we are small, brief, limited creatures attempting to understand something far larger than ourselves. The recognition that we might fail, that the universe might keep its deepest secrets, but that the attempt itself is worthwhile. Return to that photograph on the desk. 7 years, now past, now memory. Those years existed. They are part of the history of this particular consciousness, this particular arrangement of matter that briefly became aware of itself and called itself I. In a few more decades, that arrangement will dissolve. The atoms will scatter, the patterns will fade, the memories will end. But the universe will continue, it will expand, it will cool, it will evolve according to laws that operated long before I existed and will operate long after I am gone. And perhaps in that distant future, some other consciousness, some other arrangement of matter asking its own questions, will look back at this moment, this early 21st century, when we first began to seriously question whether the Big Bang was the beginning. Perhaps they will have answers we do not have. Perhaps they will have confirmed that there was a before, or confirmed that there was not, or discovered that the question itself was poorly formed, based on assumptions that do not survive a deeper understanding of reality. Or perhaps they will still be asking. Perhaps the question will remain perpetually open, a horizon that recedes as we approach it, always tantalizingly close, but never quite within grasp. Either way, the question endures, not because it is easy, but because it is fundamental. Not because we expect a simple answer, but because the universe has shown us again and again that it is more complex, more subtle, more surprising than we initially suppose. What if the Big Bang wasn't the beginning? We do not know. But we are asking, and in the asking, we are doing what humans have always done, reaching beyond ourselves, beyond our immediate experience, trying to understand not just the world around us, but the very nature of existence itself. The universe keeps its secrets, but it also leaves clues. And we, for all our limitations, are learning to read them. The question remains open, the search continues, and that for now is enough.